Okay, acids and bases. So let's take a look at the different types of acids and bases. So this is just going back to your previous knowledge. You have an arenous acid and an arenous base. And an arenous acid is one that when it's dissolved in water, we increase our H plus concentration. So if we have HCl and we put it into water, it'll break up into H plus and Cl minus ions. Whereas a base, what happens is it will increase its hydroxide concentration when we add it to water. Okay, so what is happening is in acid-base chemistry, water undergoes autoionization, and so water is breaking into H ions, H plus ions, and OH minuses, and it's going back and forth. Okay, and we can relate this to our KW, so the equilibrium for water, and that would be our OH minus concentration times our H plus concentration. When that happens, OH is, that concentration is 1 times 10 to the minus 7, and the H plus is 1 times 10 to the minus 7. So therefore, KW will be 1 times 10 to the negative 14 for water. Sometimes when you're doing reading and stuff, you'll see H3O plus, and that's the same thing as H plus, your hydrogen ion concentration, or we may call it hydronium. Those are the exact same thing. So if we wanted to find the concentrations, we would use the P, for pH or POH, we're going to use the negative log. And that's what pH, and you have POH. That P stands for negative log. So the negative log is going to, of those concentrations, is going to help us find the pH and the POH. Again, pH range is 0 to 14. Sometimes we can be on the other side of that, on other side of 0, other side of 14, but rarely. And then if we were to have the POH range is going to be reverse of what we have for the pH range. Any questions over that? Yes. So let's do some problems here. Oh, never mind. Out of order here. A strong acid, did I skip a slide or no? Okay. A strong acid, remember, is one that dissociates completely in water to have high concentration of your ions. Strong acids are strong electrolytes. Weak acids are weak electrolytes. And a weak acid does not completely dissociate. And the same thing happens with a base. Strong base completely dissociates. Strong bases are strong electrolytes, weak bases, weak electrolytes, and does not completely dissociate in water. So basically today's just review. All right, so for aqueous solutions of the following substances, write the dissociation reaction and indicate whether the substance behaves as an arenas acid or base. So HF, it's going to dissociate into what two ions? H plus and F minus. So is it going to behave as an acid or base? Acid. And what type of acid is it? Strong or weak? It's a weak acid. Yes, Lauren.
I've been getting a lot of spam phone calls lately.
All right, the next one. What's it going to break into?
I'm sorry.
H plus and C6H5O minus. So is it going to act as an acid or a base? An acid. And is this a weak acid or a weak base? Or weak acid or strong acid? Why is it weak? There's not two or more H's, and what's the biggest deal is it contains carbon. All right, the next one breaks into what? Ba2 plus 2OH minus. Is this an acid or a base? Base. Is it strong base or weak base? Strong. All right, so somebody tell me what's the difference between the two I wrote. When we took this dissociation reaction, why did I use equilibrium arrows in one and not the other? Because it's happening.
It's just chilling there until it's sealing back.
Okay.
Solid.
Solid? No.
And it's equilibrium, so it's talking about
Lauren.
Because weak acids don't fully dissociate, so there's still some going back into solid form after it dissociates.
Right. And it's not solid form, they're just they bond again. So, yes, strong acids and bases, they completely dissociate. So they do not go back the other way. So we have that one-sided arrow, or single-headed arrow. So lithium hydroxide breaks into Li plus and OH minus. And this is what type of solution? Base. And it is a strong base. What about water? It is both. So it's going to break up into H plus and OH minus. And what do we call one that acts as both an acid and a base? Amphoteric. Amphoteric.
Is there anything else that's amphoteric besides
NH3, because it can take up, but and I'm trying to think of one more. I know NH3. There's a couple of them. And then the next one, what we've been looking at is if we only have one H, it is called monoprotic. Now we have come to where we have H2CO3, and this is diprotic. And then if it has more than that, you'll see triprotic, or like we just call them polyprotic, more than one proton. These will ionize in steps. So what happens is we will get H plus HCO3 minus, and then the HCO3 minus is going to break down into H plus and CO3 minus 2. So this is a stepwise dissociation. Huh? It is, yes, because it's got carbon in it. Questions? Everybody good? All right, so calculate the pH and pOH in each of the following aqueous solutions. Indicate whether the solution is acidic or basic. So we have our H plus concentration, and we need to find the pH, and we need to find the pOH. So put that in your calculator. Negative log . 2.85. And then what would the pOH be? 11.15. And you could either use OH times H plus is equal to KW to get that, or you could do pH plus pOH is equal to 14. And what type of solution is it? Acidic or basic or neutral? Acidic. Okay. Now, what about the next one? OH minus. We want 2.08 times 10 to the minus 7. Get me pH and pOH. Give me 3 decimal places.
pOH is
6.682. And so pH would be 7.318. Basic or acidic? Neutral? Basic? Okay. I'm going to throw in some sig fig rules in here for you guys. With acids and bases. So for your sig fig rules, for acid and bases, you go however, so you take your H plus or OH concentration, so 1.4 times 10 to the minus 3. And for your pH and your pOH, you go as many decimal places as there are significant figures in your concentration. So if there's 2 sig figs, then we have to go 2 decimal places in our answer. So if you go back over here, we had 3 significant figures. So we went 3 decimal places in our pH and our pOH. And so when you're working back the other way and you have a pH that has 7.318, 3 decimal places, remember your answer has to go to 3 sig figs. So that's one weird rule about your acids and bases. Okay? All right. Next. Calculate the H plus. We're only going to do one of these, but calculate the H plus and OH minus in each of the following aqueous solutions. So this time we're going to use ten to the power of our negative pH, or 10 to the power of our negative pOH. So what is our H plus for 7.41? What's our H plus concentration? 3.9 times 10 to the negative 8, and our unit is big M, or moles per liter. So our OH concentration would be what then?
So
2.6 times 10 to the negative 7. Good.
So just whenever you do this way, do decimal places to tell you how many sig figs.
Yes. Yep. Okay, so any questions over those? I'm not going to work any more of those because it's just preview. Okay. Bronsted-Lowry acid and Bronsted-Lowry base. Remember, a Bronsted-Lowry acid or base is one that an acid is one that donates a proton, while a base is one that accepts a proton. So if we have HCl and we add it to water, then what ends up happening is the H will end up donating a proton to give us a hydronium atom or compound, and then we will take the water will accept it. So if you are an acid, Bronsted-Lowry acid, then your opposite is going to be the conjugate base. So you have an acid, and when you donate that, you become a conjugate base. When you donate a proton. The base, when it donates, or when it accepts, the base now becomes a conjugate acid. Yes?
what if it becomes neutral, like ammonia to NH3 nitrogen?
It's still the same thing. You're going to get like, so if we had NH3 and we add water, NH3 is a base, and then it can accept and become an acid, the conjugate acid, and then we would have the OH minus. Okay, so acid always has a conjugate base, and the base always has a conjugate acid. And if we were to flip it to go the reverse, now the conjugate acid becomes the acid, and the other one becomes a conjugate base.
But in reverse, both NH2 and H2O are like they're both acids and bases.
Right. So it kind of just depends because they're both amphoteric. They'll both go either way. Okay, for each of the following, write the formula for the conjugate base. So, H2PO4, what is its conjugate base? Oops. HPO4. It was a -1, now it becomes a -2. H2O. It donates a proton, so it becomes OH minus. What about OH minus? What happens there? It's a trick question. It won't. What about HClO2? It donates a proton and it becomes ClO2 minus. NH3 or CH3NH3 positive. When it donates a proton, what does it become? CH3NH2. You got rid of a proton, so the minus charge or the plus charge goes away. And what about NH4 positive? It becomes NH3.
On the one before, it doesn't matter which H you change.
Okay, so when you're looking at this, these are usually written to who they're bonded to. So there's the C, and the H's will be bonded all to there, and then the N, and then you would have the H's over here. So I would usually take it off the last one.
Wouldn't it go off the C because N is more electronegative?
But it's going to take off, no, it comes off the H, or off the N. Okay, and then what about here? We're going to do the following bases and write the conjugate acid. So OH minus becomes what? H2O. CH3, CH2, NH2 becomes what? We have our carbon backbone here. So we're going to add an NH to, or an H to the, and we're going to have a positive. Cl minus becomes HCl. H2O becomes H3O plus. And CH3,3N becomes CH3,3NH plus. I mean, I guess you could put it at the front. Because we really haven't talked about where they would be bonding at, so. All right. And lastly, we're going to take all these and add them to water. And then we're going to label the Bronsted-Lowry acid base and the conjugate acid base. So NH3, we've already seen HCl. So NH3, we're going to add it to water. When we add it to water, what are we going to get? NH4 plus and OH minus.
I didn't know which one will give us.
It would be, so we could have had this, NH3 plus H2O, and we could have gotten NH2 minus plus H3O plus. Just because NH3 is one of those weird ones that can do that. But usually you're going to know what's going to happen. So if we're looking at the first one, NH3 is our base. Water is our acid. Huh? Just by definition, Bronsted-Lowry base accepts a proton. So that means this is our conjugate acid. Bronsted-Lowry acid donates a proton.
He's asking which one do you use? Like,
Oh,
does it matter which one?
like for this one up here?
Yeah.
Oh, either one would be the right answer. And OH would be our conjugate base. So what happens in HCN? We're going to add it to water, and what are our two products going to be? Cyanide and hydronium. So which one's our acid? HCN's our acid, so CN minus is our conjugate base. Water this time is our base, and hydronium is our conjugate acid.
How did you know that? How did you know that HCN would be the acid and not the?
You look at the reaction, and by definition, we're accepting or donating a proton. So, HCN donates a proton.
Oh yeah, but like you know it's gonna be CN H3O and not H2CN plus.
Because that's just something that doesn't exist. I mean, look at the next, go to the third one. Go to E. We're going to add it to water. So what are we going to get? CH3, CH2, NH3 plus an OH minus. You have your base, acid, conjugate acid, and your conjugate base. You know what? You could probably draw that. And then determine where will I be able to, can I put another H on C? But who can take in an H? Or we could get rid of that H. So it's kind of, I don't know. I've never even thought of it, of how to.
Right, there would be remove an H because there's already 3 bonds on H. And remove out seeing, how many I have
Mm-hmm. Okay. And last slide. pH of strong and weak or strong acids and bases. So calculate the pH of a 0.45 molar HCl solution. So the first thing that you need to do is, we know it's HCl, ivory and clay, that it's strong acid. So it's going to break up into H plus and Cl minus. The pH or the concentration is 0.450 molar, which means when this breaks up, H plus is going to be 0.45 molar and 0.45 molar for my Cl minus. Which one of these do we calculate our pH off of? The H. So we need to take the negative log of the 0.45 molar to get the pH. We have 3 sig figs, so we need 3 decimal places. 0.347. Next we have KOH, which is a strong base. KOH is going to break into K plus and OH minus. Again, when it breaks apart, the molarity for each ion will be the same. So this time, if we take the negative log of our OH minus, what are we going to get? We're going to get our POH, which is 0.149. So the pH becomes what? 13.851. Any questions on pHs of strong acids or strong bases? Since it completely ionizes or dissociates, then that means that the concentration of the acid or base is equal to the concentration of the H plus or the OH minus. All right, so your homework tonight is A,